Okay, so at the end of the day yesterday, we were talking about Newton's third law in a system situation. This is usually how a Newton's third law question will go, because in a Newton's third law situation, there has to be an action and a reaction, which means there basically has to be two forces going on at all times. So with this situation, we were trying to find out how much force is exerted on box B by box C. So what we had done is we had broken down the system, okay, into the three boxes. So we had box A, right, and we knew that there was this force, that was the applied force from the hand, pushing A to the right. Because A pushes on B, okay, B pushes back on A. That's the action-reaction pair. Okay, that's the reaction part of the pair. Right? For box B, okay, we had the force of A on B. Okay, that's the action. This is the reaction. Okay, those two forces are part of a pair. And because B is going to push on C, C is going to push on B. That's the force the question wants us to find. Okay? And then for C, because this is all frictionless, there's no friction acting on any of them, we have this force, the force of B on C, and there's nothing in front of C, so that's the only force that acts on C. Everybody okay with that? Okay, so if we're trying to find out how much force C exerts on B, so we're trying to find this force, we established that A is no help. Okay? I don't know the applied force, I don't know the force A exerts on B, or B exerts on A, I don't know any of that. Box A can't help me here. Okay? Obviously the force I want to find is acting on box B, so hopefully I can use box B to find it. All right, the other thing we know is we know the mass of all of these boxes. B is 10 kilograms, C is 5 kilograms, A was 8, but we've already established we're not using A. We also know that the system is accelerating at 1.5 meters per second squared to the right. Okay, which means I can find the net force on the system or on the individual boxes because I know their mass and their acceleration. Everybody with me so far? Okay, all of that is Newton's second law stuff, isn't it? Right? Like, there's only going to be one piece of this puzzle that actually involves having to go, oh, every action has an equal and opposite reaction. Everything else is F net is m times A. F net is the vector sum of all forces. Newton's third law problems are really Newton's second law problems. Okay? The only thing that comes in is you might not actually solve for the force they want. You might solve for its action or reaction partner. Okay, and that's what's going to happen here. So yes, I can calculate the net force on box B. Okay, it's going to be 10 times 1.5. So 15 newtons, and we'll just say positive for that way. That doesn't really help me though. I don't know this force. And obviously, since they want me to find that one, I don't know it either. So I'm really stuck with box B. I can't, because I don't know either of the two forces contributing to the 15 newtons, I can't go any further with box B. So I actually can't find the force the question wants. But in this system, there is another force that is equal to that force in the opposite direction. This one. Okay? The only reason C pushes on B is because B pushes on C. Does everyone follow my logic there? Okay, so according to Newton's third law, those two forces are equal but opposite because they're an action-reaction pair. How does that help me? Well, if that is equal and opposite, the force I'm looking for, and it's the only force acting on box C, is it pretty easy to calculate? If it's the only force, it's the net force. And I can calculate that because I know the mass and the acceleration of that box. All right, so this is really the only calculation I have to do to solve this question, is to go 5 kilograms times 1.5. Okay, so 5 kilograms times 1.5 is going to be 7.5 newtons in a forward direction, so positive. Right, well, then that means that this force is negative 7.5 newtons, or 7.5 newtons to the left. Yeah, because they give us right and left, so we should say left. Okay, was there a lot of convoluted reasoning to solve that problem? And how much math? Yeah, well, I didn't have to do this, so that was the only calculation I did. One calculation, lots of figuring. Okay, so that's what makes these questions tricky, is all the figuring that has to go on. Okay? There's no hard math with these. It's just, okay, I got to draw all these forces. Who goes with who? Is this an action or a reaction? Are they the same? Okay, that's the tricky part with Newton's third law. Right? It's not going to be the math that gets in your way, I promise. Right? Okay, now, same 3 boxes. Okay, we know all the same things, including what we just found a minute ago. All right, so now we want to find out how much force box B exerts on box A. All right, so let's go back and we'll draw all our free body diagrams again, and then I'll let you guys see if you can calculate it. So this is box A, it's 8 kilograms. Okay, that's the force applied from the hand. This is the force they want us to find, force of B on A. Okay, and then we have box B. Okay, we know this force now because we calculated it. The force of C on B is 7.5 newtons. Okay, this is the force of A pushing on B, and this is 10 kilograms. And then we of course have box C, but I don't think that's going to help us very much now. Okay, 5 kilograms, that's 7.5 newtons. Okay, and we also still know this. Okay, that's all the stuff we know because we've done a little bit of work already. Okay, now let's see if we can find this force. I didn't necessarily draw my arrows to scale. Okay, don't let that mislead you. Okay, give you a few minutes, see if you can figure that one out. So this is the force that we're supposed to find. All forces act in pairs. Okay, now if I'm looking at this at box A, I don't know what this force is. I don't know what this force is. I can calculate the net force, but does that help me? It doesn't help me because for box A, F net on A is the applied force plus the force of A on B, and without knowing at least one of those, I can't calculate the other. Box A is of no use to me in this question, but all forces act in pairs. Does this force, which is a reaction, have an action pair somewhere? Where's its action pair? Right there. Okay. The only reason B pushes on A, the force we want to find, is because A pushes on B. That's an action-reaction pair. So I might be able to find this because in the last question, I found that force. So now I actually know one of the 2 forces that is acting on box B. So I can calculate the net force on B. F net is 10 kilograms times 1.5 meters per second. So the net force is 15 newtons to the right. Okay, now vector sum of all forces. Am I doing anything we haven't done before? Okay, vector sum of all forces. F net equals, okay, the force of C on B plus the force of A on B. I know that one, and I know that one. So I can isolate the one I don't know. So F net minus the force of C on B will equal the force of A on B. Vectors are important here. Okay? So my F net is right, which is positive. So I'm going to write 15 newtons. Force of C on B is left, negative 7.5 newtons. Okay, so 15 minus negative 7.5 is 22.5 newtons to the right. Now there's only two significant digits there, so it would actually be 23 newtons to the right. Okay, we had to do two calculations. We had to multiply 10 by 1.5, and we had to subtract negative 7.5 from 15. Okay, again, no rocket science kind of math there, but a lot of reasoning. Okay, and that's the skill that we want you to develop in Physics 20, is to be able to look at a situation and see what's happening inside and reason your way through it. Okay, this is about as complex as the reasoning will have to be in Physics 20, okay, but this is the building block for 30. You're going to see situations that are even more involved in Physics 30, and having this skill of being able to look at a system, figure out who's pushing on who and what the interactions look like, that's the skill we want you to have. Okay? We already know you can do math, so these don't involve any hard math. They just involve being able to discern and analyze within a system. Okay? Anybody need that one up anymore? Okay. Try that one from the beginning. Friction's involved in this one. Okay, but remember, it's just a system. It's just a Newton's second law question, except for finding an action-reaction pair somewhere. All right, I'll give you a few minutes on that. So for this one, okay, they're identical materials, but different masses, okay? And they're on a horizontal rough surface. We know their acceleration, okay, is 2.6 meters per second squared to the right, okay? Which means, since we know their masses, we can calculate the net force on the system, we can calculate the net force on individual boxes, so that's handy, okay? An applied force acting on box A causes both boxes to accelerate. The magnitude of the force of friction on box B is 28.3 newtons. Okay, calculate the force exerted by box B on box A. All right. Box A, 6.5 kilograms. There's the applied force from the hand. Okay. We know there's friction, but we don't know how big it is, not on box A anyway. And what's the other force acting on box A?
Force of B.
Force. Right, force of B. That's the one they want us to find. All right, I can already tell I have no hope of using box A to do this. I don't know what this force is. I don't know what the force of friction is. I'm looking for that force. There's no hope of using box A to find any of that because I know virtually nothing about box A. All right, let's look at box B. Maybe box B can help us. Okay, the only reason B is moving that way is because A pushes on it. What's the relationship between this force and this force? They are the same. Opposite in direction. They are an action-reaction pair. This is the reaction, this is the action. Okay? All right, maybe we'll be able to use box B to find that force. What else is acting on this 8.5 kilogram box?
Friction.
Friction. And they told us the value of that. It was 28.3 newtons. Okay, and what's the other force acting on box B?
The opposite reaction of force on the first box.
There's a trick. There was no other forces acting. Those are the only two, right? There's nothing in front of B. Okay, so the only force pushing on B is A, and friction is resisting it. Those are the only two forces. Okay, well that's good because I know the mass and the acceleration. What can I find? The net force. Okay. So F net is mass times acceleration. Okay, we got 8.5 times 2.6. Oh, I forgot to fire that up. Okay, what's 8.5 times 2.6 get out there? Finally fire that. What is it? 22.1? Okay. Okay, so 22.1 newtons to the right. Okay, now, vector sum of all forces, like we do for any other problem, right? Force of A on B plus the force of friction. So if I want to find the force of A on B, I subtract the force of friction. So F net minus FF equals the force of A on B. So that will be 22.1 newtons minus negative 28.3 newtons. Okay, because it's backwards, right? Vectors matter here. All right, so we're looking at what, 40.4? 50.4. 50.4. Okay, 50.4 newtons to the right. That's the force of A on B. What's the force of B on A?
50.4 newtons left.
50.4 newtons to the left. Okay, we've done way harder Newton's second law problems than this. Okay, what's tricky is sorting it all out and getting to that. Okay, is that the kind of thing I could put on a unit exam? I would absolutely put a 2-box Newton's third law problem on a unit exam. Okay, because what is it asking you to do? Newton's second law. Really, that's what it comes down to. Okay, I want you guys to try this one with the logs. Okay, the team of horses pulling the logs. I'll give you a few minutes on that one. Okay, so 2 logs and pulling, same as 2 boxes and pushing. Doesn't change anything. It's still a Newton's second law / third law situation. Okay, we have 2 logs. The 250 kilogram log and the 150 kilogram log. Okay, and then we have obviously the force applied from the horses acting on the back. Now, first thing it tells us is that the horses can pull with 2,600 newtons. Okay, so I know that force forward, and then it says the force of friction on the logs, plural, is 2,400 newtons. So I'm just going to simplify this and say 400 kilograms is being pulled this way by an applied force of 2,600 newtons and resisted this way by a force of friction of 2,400 newtons. What is this going to help me find right now?
Acceleration.
The acceleration. If I can find the net force on the system, which is 200 newtons forward, okay, and I know the mass of the system, I can calculate the acceleration. Once I know that, I can apply it to the logs individually, which is what we did in the other ones. Okay, so F net, okay, divided by mass, 200 newtons forward, divided by 400 kilograms, is going to give us 0.5 meters per second squared forward as the acceleration of the system and its individual parts. Okay. Now that I know that, I can go on to part B. Okay? And in part B, it's if the force of friction on log A is 900 newtons, calculate the force exerted by log B on log A. There's actually 2 ways to do this. Okay? I can use either log to calculate this. A is a little bit quicker. All right, so let's break this down to the 2 logs. Here's log A, 150 kilograms. There's 2,600 newtons worth of force going forwards from the horses acting directly on log A. There's also a force of friction of 900 newtons acting backwards on log A. They tell us that specifically. And what else is acting on log A? Log B. They're attached by a chain. Okay? Through that chain, there's a force of log B on log A. Okay, well, I know 2 out of the 3 forces acting on that log, and I can calculate the net force acting on that log. Agreed? Okay, well, let's calculate the net force on that log. F net is 150 times 0.5. So the net force on that log is 75 newtons forward. Okay, since I know that, now I can do vector sum of all forces. F net is the applied force plus the force of friction plus the force of B on A, which is the force they want me to find. Okay, so I'm just going to subtract the other two forces over. So I'll have F net minus the applied force minus the force of friction equals the force of B on A. Vectors are important here. Okay, the 75 newtons is positive. So is the 2600 newtons. So I'm actually subtracting a positive number there. And then I am subtracting negative 900 newtons, the force of friction. Okay, and if I do that, that comes out to 1,625 newtons, I believe, backwards. But there's only 3 significant digits. So 1.63 times 10 to the 3 newtons back. Okay, everyone follow my logic there? Did anyone solve it using log B? Okay, so we could have done this with log B as well, right? Process is the same. Here's the force of A on B, which is the action-reaction pair to the force of B on A. Okay, and then there's the force of friction. Now, they don't outright tell me what the force of friction is, but they previously told me the total friction was 2,400, and I know that 900 of that was on the front one. Okay, so that should leave me with 1,500, right? 1,500 back. Okay, well, I can still do this. F net is m times A, so 250 times 0.5 is 125 newtons forwards. Okay, is my net force, and then F net is the force of friction plus the force of A on B, which is the action-reaction pair. Okay, and then we just do the subtraction operation here. So we'll have F net, okay, minus the force of friction, okay, equals the force of A on B. So our 125 newtons minus negative 1,500 newtons, right, is going to give us 1,625 newtons, but this time forward, same force, just different perspective. Okay, either way gets the right answer. Okay, everybody follow me on the Newton's third law stuff. Okay, so expect you're going to get a 2-box question like any of these that we've done today on your unit exam as an assessment of that, because it is, after all, really just Newton's second law. The only thing is, at some point in that question, you'll find the pair instead of the actual force, and then use it to know the actual force. Okay. All right, I'm going to give you guys here about a 3-minute break, and then we're going to start talking about work energy theorem, okay, which is like the second, well, the last third of this unit, we'll say. Okay, so I'll give you a couple minutes, and then we'll get started on it. Okay, so work energy theorem. We covered this in Science 10. Okay, we actually spent quite a bit of time on it in Science 10 physics. Okay, work energy theorem says that work is a change in energy. All right, and that fits well with what we're doing right now with Newton's laws. If you're going to accelerate an object, that's going to require a force. And forces exerted through a distance require energy, work. Okay, so from Science 10, we already know that work is a change in energy. And to change the energy, you must exert a force through a distance. Okay, all of that is stuff we did in Science 10. The work energy theorem, the concept of it, doesn't change. Right? In Science 10, we only had to deal with situations where the work we did changed either the potential energy of an object, so we lifted an object, okay? Or change the kinetic energy of the object. May the object go faster or slower. Okay? In physics 20, we'll deal with situations where both types of energy change. Because when it comes down to it, work isn't a change in kinetic or potential, it's a change in mechanical energy. Okay? And remember, we calculate mechanical energy by adding potential and kinetic together. Okay? So that means if I do work, it's possible to change both an object's potential and kinetic energy. Like if I throw something up in the air, okay, I'll definitely be changing both its speed and its height. Okay? Is that ringing a bell from last year? Okay? So we're going to just be looking at that, but we're going to be looking at it from a situation of now, let's look at a real world situation where both kinds of energy are going to change. Doesn't really change anything for us, just we have to keep track of two energy types instead of one. Okay, now, if I push on an object, okay, and it moves, do I do work? Most of the time, yes. What if in pushing that object, okay, or let's say pulling that object as I'm doing right now, makes it move at a constant speed? Am I doing any work on the cart? See some more puzzled looks up there for that one. Okay? If I don't change its speed and the floor is level, have I changed the energy of the cart at all? I haven't, right? If it's going at a constant speed, its kinetic energy isn't changing because its speed isn't changing. If I'm not lifting the cart, I'm also not changing its potential energy, right? But I would argue that while this thing is moving at a constant velocity or constant speed, I am still doing work. It still takes energy for me to push it. I'm not doing work on the cart. I'm doing work against other forces, like friction. That's why it makes noise. Okay? The noise is evidence that I'm doing work. I'm just not doing work on the cart. I'm not changing the energy of the cart. I'm changing the energy of the surroundings. Sound and heat and stuff like that is going up in the surroundings. I'm doing work, but I'm not doing it on the cart. In order for an object to experience work, its energy has to change, which means it either has to go higher or faster or slower. Okay, does that make sense? Okay. All right, so when work is done, when a force is exerted through a distance. I did work in pushing the cart, okay? Not on the cart, but I did work. Energy went from me to other places. That's work from my perspective. Now, if I grab this cart and I accelerate it, have I done work on the cart? Definitely, because its velocity would change. And if its velocity changes, it accelerated. That means kinetic energy changed. That's work on the cart. The cart now has more energy than it had before I pushed it. Okay? When I'm moving it at a constant velocity, it has the same amount of energy all the time. Okay? That's why technically it requires no force, no net force to move something at a constant velocity. You're not changing its energy if it's moving at a constant velocity. You'd be doing work on the surroundings instead. Okay? So if I'm doing this, okay, and I push that car, okay, and it accelerates, then I'm definitely doing work. Agreed? And what kind of energy am I changing about the car, assuming that that's a level surface? Kinetic, because its speed is changing. Okay? What if I was pushing it up a hill? I wouldn't just be changing its kinetic, I'd also be changing its potential, because, well, don't ever push a stalled car up a hill, because it could roll back over you. Okay? Because if you push it up a hill, you're giving it the potential to roll back down the hill. Okay? And that's, from a physics perspective, probably not wise. Okay? Now, what if I push it up the hill at a constant speed? Am I still doing work? Yeah, I'm still changing its potential energy. I'm making it higher. Okay, by making it higher, I'm giving it the ability to come back down. That requires energy from me, I'm giving it to the car. But I'm not changing its kinetic anymore because I moved it at a constant speed. Those are the things we have to watch for. Okay? Being able to identify what types of energy is changing is the key part of work energy theory. Okay? A force is being exerted through a distance. Okay, work's being done. What kind of energy is that work changing in this situation? Okay? That's that analysis skill or analytical skill we want you to have. Okay, now, in Science 10, you learned that work is F times D, which is slightly simplified from what the work energy theorem formula actually looks like, which is this. Okay? We very rarely ever have to use the cos of theta part. You only need that if you're exerting a force in a direction different from the object's movement. Okay? So that could be if I am dragging the desk. Okay? If I lift the desk and drag it like this, okay, the desk is moving horizontally, but I'm lifting it a little bit. Okay? But since, okay, if we just consider I've lifted it and now I'm pulling it at an angle, I'm not changing its potential energy, am I? It's not moving vertically, it's moving horizontally. Okay? That is where only the horizontal component of my force is actually doing any work. That's when you would have to use this. Okay? You have to bring that in if the direction of the force was different from the direction of the movement. Only the part of the force going the same way or parallel actually does work. Okay? Just a vector analysis of that. Now, on that note, vector analysis. Is work vector or scalar? Scalar. Work and energy are scalar because once you do the work, it's changing energy. Energy is also scalar. Energy is something you have. Okay? It is the ability to do work somewhere else. It doesn't have a direction. I mean, think of it from a, not a physics perspective, but a chemical energy perspective. If I eat a big meal that contains 2,000 joules of food energy, okay, I don't say I ate 2,000 joules of food south. It's gonna go south, okay, oh, it's gonna end up here, okay? But it's not, it doesn't have a direction. I now have that much more energy than I had before. I can use that to do all kinds of things, like nap if I want to, because I'm old, okay? Or maybe I'm gonna, walk down the hall to the photocopier room. That's gonna require some of the food energy that I consume. It doesn't have a direction, it's just giving me the ability to do things, okay? So work and energy are scalar quantities. You will never put a direction on them, except from the work perspective. Work can be, even though it is scalar, positive or negative. It depends on whether you're doing the work or the work is being done to you. Okay, so it's not a matter of direction, it's a matter of gain or loss. Okay, if I push on the cart, from the cart's perspective, that is positive work. It gains the energy I do. From my perspective, it's negative work. After pushing the cart, I have less energy. Okay, so work can be positive or negative. Energy, no. Okay, energy is scalar, okay, entirely. But work, from a perspective standpoint, can be positive or negative. Okay, I think that covers everything on that slide. Okay, now, units for work are a Newton meter. I mean, after all, okay, it's force times distance equals work. So force is in newtons, okay, times distance in meters, okay, that's going to be a Newton meter. Well, they can break down further than that, can't they? right? Because a Newton is actually a kilogram meter per second squared. Okay, you multiply that by meters, and you have kilogram meters squared per second squared. That is a joule. Okay, so the units for work and energy are joules. The fundamental units of a joule are a kilogram meters squared per second squared. Okay, you never have to write it like that. Okay, just write J, that'll be fine. Okay, but know what a joule is. Okay,
Newton meters.
a Newton meter, which is a kilogram meter squared per second squared. Okay, it only matters if you're breaking something down, dividing work by something else. You have to know what your units are going to be after that. Okay. All right. Now, these girls here pushing on that rock. Are they doing any work on the rock? That rock ain't going anywhere. Doesn't matter how hard they push on it. Okay? That rock is not going to change its energy. It's mechanical energy anyway. If they keep pushing on it, where they push will get warmer. Okay? But that's heat, right? That's a transfer of thermal energy. It's not giving the rock the ability to do any work. It's not gaining any energy. Everyone okay with that idea? Okay. All right, so this is that F cosa theta thing. It's the situation where it could come into play. Okay, if you're dragging, let's say, you're rolling luggage through the airport. Okay, you're probably got it angled behind you. Some people set it in front of them and roll it like this. Okay, but we're going to say we're dragging it behind us at an angle. Right? If we exert force through that handle, that force is directed this way. But the cart's movement, or the suitcase's movement, is this way. Right? Since we're using a vectored force, which is a vector quantity, okay, we have to realize or account for the fact that the vertical part of that angled force isn't doing anything. Okay? The potential energy of the luggage isn't changing because the height of the luggage isn't changing. Right? If we're dragging it down the airport hallway, we're doing work, but it's horizontal. Everyone okay with that idea? Okay. So if we get some numbers in here, okay, let's say that the force in the handle is 45 newtons and the angle is 50 degrees. Okay, so this is 45 newtons. This angle here is 50 degrees. Okay. She drags it 75 meters. How much work is she going to do? Okay, so F cosa theta times D. So our 45 newtons times the cos of 50 degrees times the distance, 75 meters. Okay, she is going to do 2,170 joules worth of work. Now, if we look at that from strictly a physics perspective, dragging that thing along the floor should make it do what? Okay, yeah, it might. That's thermal. I'm saying from a physics perspective, if she's applying a force on it, it should accelerate. She should be changing its kinetic energy. Guys, if you accelerate that luggage using that much force for 75 meters, you are going to be probably running faster than the fastest human. Okay? So realistically, that's probably not what is happening in the real world. What Chase said is probably what's happening in the real world, and that is that it's going to accelerate a little bit, but eventually you're not going to walk much faster than you're walking, and the rest of the energy is going to be lost to the surroundings as heat, sound, okay, things like that. All right? She's still going to do that much work. The suitcase isn't gaining all of it. Okay? In the real world, the suitcase isn't gaining all of it. So we're going to do lots of problems with what's going on from a strictly perfect physical world perspective, but we need to understand that in the real world, some of the energy is going to be transferred to the surroundings. Okay, we call that work against non-conservative forces. All right, everyone follow how that one worked? Okay. Now, let's say you're working out, doing a bench press. Okay, the weight of the barbell is 710 newtons. So if I want to move it upwards at a constant velocity, how much force do I have to exert? Yes, 710 newtons, right? If it's going to move at a constant velocity, the net force needs to be 0, okay? From a free body diagram perspective, okay, there's the barbell. I push up with 710 newtons. Gravity pulls down with 710 newtons. Barbell moves up at a constant velocity, right? That means I'd only be changing its what kind of energy? Potential energy. I'm not accelerating it, I'm just moving it upwards. So, how much work am I going to do if I lift that barbell 710 newtons, 0.65 meters? Okay, so let's have a look at that. F cosine theta times D equals work. Now, I'm pushing straight up. The barbell is moving straight up. What's theta? 0. They're parallel. What's the cosine theta? What's the cosine of 0, sorry? 1. Okay, so does this even matter in this situation? Okay, so I can just go like this. Force times distance, right? Okay, it's going to equal work. So 710 newtons times 0.65 meters. Okay, so that's going to be 462 joules worth of work. All right, so now the barbell has 462 joules worth of potential energy. I probably don't want to drop that. Okay, 462 joules of potential energy could very quickly become 462 joules of kinetic energy, which could do work on me, okay, and change my shape in an undesirable way, like, you know, making my rib cage a lot flatter. Okay, so I probably would not want to drop this thing. So on that note, I've lifted it. Now what do I do with it? Okay, I mean, if I'm working out, and I see people work out wrong all the time, no offense guys, but especially young men, okay? I see them, because I used to be one, work out wrong all the time, okay? They put the weight on that thing, and they push it as hard as they can up. Boom, yeah, I'm awesome, and then they just kind of let it fall back onto the rack, okay? If you let it fall back onto the rack, you've cheated yourself out of half the workout. Okay? When you lift weights, are you supposed to lift nice and slow? Okay? Evenly up and down, right? Why is the down part important?
Your muscles under contraction.
Yeah. Okay? If you lift hard, sure, your muscles do work, obviously, to lift the weight. You want them to do the work to lower it, too. Okay? If you lower it slowly, are your muscles activated? The whole time, right? Okay? If you just go, what was the point? Okay? You're going to have to lift it twice as many times because you're not doing any work in the downward direction. Okay? So, let me say that again. You're not going to do any work in the downward direction. So, I do work when I lower this thing?
So you want to drop it on
Unless you want to drop it on your chest, yes, you do work when you lower this thing. Because you still, if you want to lower it at a constant velocity, have to exert how many newtons of force upwards?
700.
710. Now, let's talk about this from the barbell's perspective. When I lift the barbell, is the barbell experiencing positive or negative work? Positive work. It gains 462 joules of potential energy, of mechanical energy. Well, when I lower it, okay, if I just drop it, it'll convert all of that to 462 joules of kinetic energy and crush my rib cage. I don't want that. So where does the work go if I lower it slowly? still back to me. Okay? From the barbell's perspective, when I lower it, does it lose the 462 joules of energy I gave it? Yeah. When it comes back down to a height of 0, the energy I gave it is gone. That energy has to go somewhere. Okay? Well, it goes back into you. You have to work against the weight of that barbell. All right. From the barbell's perspective, we said that work was negative on the way down. Okay. If this, my force and the direction of movement are 0 degrees, when I lower it, I'm still pushing up, but the movement is this way. How many degrees are there between the direction my force is pushing and the direction the barbell is moving? 180 degrees. What's the cos of 180? -1. So if I go 710 newtons times the cos of 180 degrees, because that's the angle between the force and the motion, okay, I'm going to get the work to be negative 462 joules. From the barbell's perspective, it's losing that energy. It's doing work on you. It's changing your shape, but this time in a desirable way. It's making your muscles shorter. You have to contract against them. Okay, when you're lowering that thing back in, your muscles are going to be shorter. Okay, when you're extending it out like this, I mean, yes, the extension muscles are shorter, okay, but when you're lowering it back down, they're contracting. They're still working against it. And there's going to be some heat, sound. You're going to grunt and groan as you lower it. Okay, all of that stuff. Does that sort of make sense? Okay, so work can be positive or negative depending on your perspective. Okay, from the perspective of the barbell, when it's lifted, it gains it. When it's lowered, it loses it. Okay? All right, what do we got for time? Good. Okay, so that's what we just talked about there. We'll skip over that. That's the math of what we just did. Okay. All right, so in order to do work, according to work energy theorem, in order to do work, you have to have energy. Okay? Physics doesn't work like the bank. You can't float a loan. Okay? Work is a transfer of energy. So if I do work on something, I can only give it as much energy as I have. I can't overdraw. Okay? It's not a credit card. I can't use more than I actually have. Okay? So, you know, it snows a little bit more this weekend. Your parents send you out to shovel. And you say, oh, I don't have any energy for that. Well, you're lying. I mean, if you're alive, you have energy. Okay? You just don't want to. But if you literally had no energy, you obviously wouldn't be able to move any snow. Okay? Because you wouldn't have the ability to exert a force through a distance and actually move things. Okay? When we say we have no energy, technically, we're not being truthful. Okay? We have chemical energy stored in our body. Now, if I lay flat on the floor, right, I would be truthful in saying I have no mechanical energy. Because when I'm laying on the floor, I can't fall any further, and I'm not moving, so I don't have any kinetic energy. Okay? In that situation, I would have no mechanical energy. So if something is going to do work, it either has to be in a position where it could fall, perched high above the ground, or in motion. It has to have either potential or kinetic or both. Okay? Everybody okay with that idea? Okay. And it could, if it transfers all of its energy, all of its mechanical energy, okay, do that much work. If it had 500 joules of mechanical energy, it could do 500 joules worth of work on another object, but no more. Okay, reminders of a couple of things. Okay, formulas that we learned last year. Kinetic energy and potential energy. Okay. Their sum total is mechanical energy. That's not on here, so we'll put that on there as well. Okay, so kinetic energy and potential energy are both affected by mass. Okay, so mass can affect your energy. And then for kinetic energy, your speed can affect your kinetic energy. But speed is, well, it's scalar, but in the formula, it's squared. Okay, so that means that speed has an exponential relationship with kinetic energy. Okay, that means an object, a 10 kilogram object moving at 2 meters per second versus a 10 kilogram object moving at 4 meters per second, it doesn't have twice as much energy, it has 4 times as much energy. Okay, if you double your speed, you don't have 2 times as much energy, you have 4 times as much energy as you had before, because speed is squared in the formula, which means it has an exponential effect on the amount of kinetic energy you have. Okay, if you triple your speed, you have 9 times as much kinetic energy. Okay, it's something we don't always think about, but it's 100% true. Okay, that is why we have the speed zones that we have in town. Okay, it's why playgrounds and school zones are 30 kilometers an hour versus the rest of the town being 40 or 50, or maybe if you're on a big road, 60. Okay, you are going to take a lot more distance to stop the higher the speed you're traveling. In fact, that relationship is also exponential. Okay, if you are moving at 2 meters per second versus 4 meters per second, it will take you 4 times as far to stop if you double your speed. If you triple your speed, 9 times as far to stop. Okay, so you got to consider that when you're driving. Okay, speed exponentially affects your stopping distance. Okay, it's a big deal if you're ripping through a playground zone at 60 kilometers an hour. Not that any of you would do that, please, God, don't do that. Okay, it is going to take you 4 times as far as it should for you to stop if you do that. Okay, so go slow through the playground zones and the school zones. Okay, construction zones, same thing. It's why all construction zones are 50. Okay, even if it's on the QE2 where it's 110, or maybe in the future it's 120. I don't know. Okay, apparently that's a thing now that they're talking about. So, okay, making sense? All right, so tomorrow what we'll do is we'll start out looking at some work energy theorem problems. We'll probably spend this week and maybe Monday, okay, working on work energy theorem. Then we'll do conservation of energy for a couple of days. That's exactly the same as what you learned in Science 10. There's 0 change there, so we don't need to spend a ton of time on that. And then we'll talk about power, and then we're done. Okay, so unit exam is December 1st.
Which is
A week from Monday.
Monday.
Okay? All right. Okay, remember guys, Newton lab reports are due tomorrow. Okay, Newton assignment due on Monday, so make sure you got those 2 things, right? Tomorrow's the 19th, is it not? Today's, oh, those were due today. Never mind, they were due today. I hope you handed them in. Good thing I reviewed that, or I would have forgot to mark them. Okay. Sweet, it's like a day further than I thought it was. This week will be over before we know it.
Made me think it's Tuesday.